This video is for section 5.2. So continuing on talking about integration, areas, and distances. But in this section, we're going to introduce the actual integral definition. So PowerPoint. Slideshow. Here we go. So the definite integral. So now we're going to take it a step farther. Last section 5.1, we broke up the area under the curves by drawing rectangles, and we recognized that they were sometimes overestimates and sometimes underestimates. Now, we have seen that a limit of the form, such as this one, here we have the limit as the number of rectangles we use approaches infinity. Recall, if we used 4 rectangles, we had quite drastic over or underestimates, meaning areas that were accounted for or not accounted for in the total area calculation. So as our rectangles increased, we noticed that the gaps of overestimate slash underestimates reduced drastically. So this is saying, well, how about we keep increasing the number of rectangles until we virtually do not have under or over estimates anymore. So this states that we are increasing the number of rectangles to as big as we possibly can, where we start at one rectangle all the way to the nth rectangle. We take the height and we multiply it by the width. Now remember, width does not change. It is constant, but the heights change based on the function and based on where you are calculating the height from, the left-hand point, the right-hand point, or we're going to introduce in this section, the midpoint. So the definition of a definite integral is exactly this. We have this fancy little symbol here. It's called the integration symbol, the integral sign, and it is created by a guy named Leibniz. I'm probably butchering that name, so I apologize. I know how to pronounce it too, but it's just not coming to me, and I highly doubt that's how you pronounce it. But he created this integration symbol, and so instead of doing this is a lot to take in when you look at it with your eyes, he simplified the symbol and said, okay, this is essentially what we're doing. We're increasing the number of rectangles as big as we can, and then we are adding we are adding the height times the width. I mean, it's literally adding the rectangles together as we increase the number of rectangles we're using. And this is a much more simpler way to look at it. We're saying, hey, there's some function. We take the antiderivative and then evaluate the antiderivative from A to B, we will be able to do exactly this. Okay, so integration is in replace of adding up length times widths for many, many multiple rectangles. The notation, the integral from a to b of f of x dx. F of x is called the integrand. It's the function after the integral. The sign itself is called an integral. A and b are called the limits of integration. A is the lower limit, where we start integrating, and B is the upper limit, where we complete our integration. For now, the symbol dx has no meaning by itself, but remember that well, I don't know if it's let's learn that dx represents, it stands for this function, f of x, is a derivative of some other function in terms of x. That's what dx stands for. Okay, the second note that I want to note is that the definite integral from a to b of f of x dx is a number. It's an area or a distance. It does not depend on x. In fact, we could use any letter in place of x without changing the value of the integral. We can use r, but you guys should know that the actual variable that we put in replace of the function itself is irrelevant. It's a placeholder for some number. Okay, this integration that is by definition equal to this sum when we take the limit is called the Riemann sum, which I mentioned in our last lecture on 5.1. actually pronouncing that one correctly. So definition 2 says that the definite integral of an integrable function, so something that actually you can take the integration of, can be approximated to within any desired degree of accuracy using Riemann sums. We know that if f happens to be positive, then the Riemann sum can be interpreted as a sum of areas of approximating rectangles, like we did last class, last lecture. We see that the definite integral can be interpreted as the area under the curve from A to B, as we practiced in 5.1. If f takes on both positive and negative values, then we are actually subtracting the area that falls below the x-axis. So this picture is great. You'll see that the blue areas when we integrate are going to be positive numbers, and this yellow, orangey gold color, peach, tan, I don't know what color it is, this color other than blue, the not blue area, is negative. Okay, so when we put this together, if the negative area is bigger than the positive areas, the overall area is going to be negative. If the positive areas are bigger than the negative area, then the overall area is going to be positive. And if they're exactly the same size, you're going to have an integral that comes out to be 0 because the positive and negatives cancel each other out. Now, let me walk you through why we have positive and negative areas and how the heck does that apply to real life. So if we take a look, let's say that, let's do this in terms of distance. So let's say here's home. Okay, we are all social distancing right now, so there's not much to do. So let's say that Johnny wants to go for a nice bike ride. I am not the best drawer, so you guys are going to get my interpretation of Johnny, a person, on a bike. Okay, here's Johnny on a bike. We get the point. He is going and he decides he's going to go to Cumberland Farm to get himself a snack. Because he's bored. We're all bored. We are social distancing. So Johnny drives his bike in one direction. Here's our starting point. And Johnny is going to the store. Now, if we were to calculate the integral from A to B, our area would be 100% positive. It would be positive area because it is showing that Johnny has traveled a total distance of whatever this is from A to B. Now, when we get a negative area out of our integral, it's because that negative area is how far Johnny is traveling back to the starting point. So there's two different types of distances. There is a total distance. Let's say that Johnny stops here because he meets up with Ava. Okay, so Ava, pretty Ava, was hanging out over here. And so Johnny went to the store, got a snack, and then ran into Ava and decided to hang out with Ava. So here is where he stops, right here. X marks the spot. Now, if we calculated this, if we saw this as a function, what would happen is we would see, do I have room here? Okay, if we were looking at this as a function, and you know what, I don't want the negative side, so I want this. Okay, now if we see this as a function, we would see that Johnny went from A to home to the store, B, and then, let me draw that again. Uh, so he went from home A to the store B. I needed to give myself more room. Then after B, he decided to start going back home and he stopped here. Ava is hanging out with some Ava. Okay, and let's call this is X. So we labeled it X. So we can see that if we calculated this integral, we would get positive here and negative here because it's under the x-axis. Now, if we did an integral from A to X straightforward of Johnny's travel, what we would see is that it would come out still a positive area. We would get this, and this is called displacement. Displacement. So what if you wanted to calculate where is Johnny's GPS location? X, Ava. You would calculate an integral straightforward, and you would have this negative area taking away from the total positive area in order to calculate X, Johnny's displacement. Exactly how far away is he from home, from his starting point? Now, let's say that we did not care about displacement, that we wanted to actually calculate total distance. Trying to delete this stuff out of the way. Hold on one moment. So instead of displacement, let's say that we were like, I don't care that he's hanging out with Ava, so that's not important to me. What's important to me is far is Johnny, how far did Johnny go today? Because maybe I'm trying to calculate well, he's not walking, but my distance, my athletic ability, my activity for the day, because again, we're social distancing and it's very easy for us to sit and do nothing all day. So in order to calculate total distance, instead of displacement, not GPS location, but instead how far did he actually travel, we would actually have to split the integral at B. So we would have to take the integral from A to B straightforward, no issues because that's all positive area. But we want to add the area as he returns back. And we know that if we did it right away, that's actually going to be negative area and it would subtract from what we calculated from home to the store. We want to add from the store to point X. So we're going to take the absolute value of the store B to Ava point X and calculate that distance and take the absolute value of it in order to get a total distance. So displacement, no absolute values needed. It will give you GPS location of where Johnny ended up, how far away he has left to go home. If we want total area, we need to find the point at which he turned around and started heading back towards his initial starting place, and place absolute values amongst that piece of the function. Okay, so that's kind of why we have negative and positive area alike. Back to the PowerPoint. So when we take the limit of the Riemann sums, we get the situation illustrated below, okay, with the positive and negative area. A definite integral can be interpreted as net area. That is a difference of areas. So here, this is net area. You are calculating everything from A to B, not even thinking about the negative area. And again, that's going to give you displacement or net. If we wanted total area, we would have to find this point, the exact point at which the positive turns negative, and we would have to find this point. And we'd have to break this up into three separate integrals: the area from A to point X, the area from X to X2, and then X2 to B, placing absolute values around the middle interval. Let's practice evaluating said integrals. Now, this is going to use a combination of our antiderivative section 4.8 from last week and some new parameters that we have to add in. So for our very first one, let's evaluate the function from 0 to 3, x cubed minus 6x dx. Okay, so now we are applying our idea of the rectangles to integration. So let's do this one out. So we have the integral from 0 to 3 of x cubed minus 6x dx. Now, it's not asking us to do any absolute values or total functions. If it's not an application problem that asks for total area or total distance, then you do not need to worry about finding out whether there's positive and negative area involved and doing any splits. That's only for application problems. So recall from 4.8, we take antiderivatives. So this integral says, hey, you need to go backwards. You need to take an antiderivative And this dx says that, yes, this is not the original function. This is a derivative of a function written in terms of x. So we take the antiderivative, we get x, we add 1 and divide. So we get 1/4 x to the 4th minus, add 1 plus 1 gives us x squared, and divide. So that gives us 6/2x squared, which we'll reduce to 3 in a moment. We're still evaluating this from 0 to 3. Notice that in this step, since we've already taken the antiderivative, the integral symbol is gone and the dx is gone. Those do not continue once you've taken the antiderivative. They disappear. This shows that we have not evaluated it yet. We are calling these definite integrals in this section, and definite means that we actually have parameters from 0 to 3. So it is not a function coming out of this, it is a value. Now, how we continue to evaluate is we have to do b minus a. So we substitute 3 in for every x and subtract, substituting 0 in for every x. So let's do that now. So we have first taking this and putting a 3 in for every x. I'm going to change that 6 divided by 2 to a 3 to make my math a little easier to look at. Weird. Okay. Minus, now do the same thing but put 0 in for every x. And since every term has an x, this is actually just going to be 0, but let's write it out for our notes for the first time. 4th minus 3 times 0 squared. Okay, then you just pop this into your calculator. So we have 1/4 times 3 raised to the 4th power minus 3 times 3 squared minus 0. Essentially, this right here is 0, so we really don't need to look at that at all. And this first part comes out to be negative 6.75. So we have to, knowing that this is a negative area, we know that there is more area under the x-axis than there is above the x-axis. So negative 6.75 is the answer to this integral. Let's do our next example. So example 2, we have the square root of x from 0 to 16. Square root of x from 0 to 16. Okay. So we have the integral from 0 to 16 of the square root of x dx. Okay, well, first thing we want to do is take the antiderivative. Remember, we have to do a rewrite first, so we haven't done the antiderivative yet. All we've done was write in exponential form. Notice that the integral symbol and the dx are still there because we did not integrate yet. We've just gone from radical to exponential. Now that we're in exponential form, we can add 1 and divide to get our antiderivative. So our antiderivative, when we add 1 to 1/2, we get 3/2. When we divide by 3/2, we do the reciprocal. So we have 2/3 x to the 3/2 power. And this still needs to be evaluated from 0 to 16. No more integral symbol because I've already taken the antiderivative. No more dx because this is no longer a derivative of a function. This is the original function. Now we plug in 16 first. So we have 2/3 times 16 raised to the 3/2 power minus 2/3 0 raised to the 3/2 power. Now this is just going to be 0, so we can ignore that. So now let's put 2/3 times 16 raised to the 3 divided by 2 power, and we get 42.67, or 42 2/3. That is the area of this example. So it's positive, so we know that there is much more positive area than negative, if there's even negative area at all, which if you know about the square root function, there is no negative area. It's all above the x-axis. Let's do our next example. So our next example is the integral from 0 to 5 of e to the x dx. All right, whiteboard, let's go. Okay, we have the integral from 0 to 5 with the exponential function e to the x. Now, this one you guys should be happy about because remember the derivative of e to the x is e to the x, and so is the antiderivative. So we have the antiderivative being e to the x. We no longer need the integral symbol or the dx because it's no longer a derivative of an original function. This is the original function. And it still needs to be evaluated from 0 to 5, where we always do the upper limit minus the lower limit. So we get e to the 5 minus e to the 0. E to the 0 is just 1 because anything raised to the 0 power is 1. So we have essentially our overall answer is e to the 5th power, which is just a number, minus 1. If you wanted an exact answer, you would just leave it exact. I love exact answers. You're more than welcome to leave it exact. But if you need it for like an application problem, you probably want to know what this is as a number. So if we put in our calculators, it comes out to about 147.41 if we needed the area or the distance traveled. Let's see if we have another example to do together. Okay, we do. Next example, we have from 0 to pi of trig, your favorite, cosine of x. So let's do this one together. So we have the integral from 0 to pi of cosine of x dx. All right, the antiderivative. Remember, what function, when taken the derivative, gave us positive cosine? Well, that would be positive sine of x. That's the antiderivative. And we're still evaluating from 0 to pi. So we put pi in the upper limit first. So we evaluate sine of pi minus evaluating sine of 0. So if you think about our unit circle, pi is at the top of the circle. So if you think about our unit circle, here's 0, here's pi over 2. Sorry, I mean, it's all the way to the left. Here's pi, here's 3 pi over 2, and here's 0 is the same thing as 2 pi, the beginning of the circle. Beginning, end of the circle, same thing. So if we're doing sine of pi, so remember, these are just points on a coordinate plane, where this is the point 1, 0, where we're always, the x is always cosine and the y is always sine. This is the point 0, 1. This is the point -1, 0. And we have 0, -1. So sine is always the y value. And here at pi, sine of pi is 0. So 0. And then at 0, sine of 0 is also 0. So we have 0 minus 0, which is 0. All this means is from 0 to pi, we have equal amount of area above the x-axis as we have below the x-axis. Okay, and actually, does it make sense? That would be 0 to 2 pi. We would have a full cycle and have, let me take a look at the graph. Let's take a look at the graph together. Let's jump to one of my internet windows and let's go to Desmos. We've used Desmos in class before. And let's take a look at this sine function. Sine of x from 0 to pi. I know I can change. Oh, I cannot remember how to change the domains of these things. I think 0 to pi. Let's see if that works. Oh, I don't remember my notations of this thing and how to change the x-axis. Graph settings. Let's see. We want. Hmm, darn. These radians, definitely radians. Let's put pi over 2 as our steps. There we go. I did it. Yay, me. Okay, so now we have it in terms of radians, and we can see from 0 to pi. So something went wrong with my calculations and how I figured them out, because all of this area from 0 to pi is above the x-axis. It should be positive. We should not have gotten 0. It would be 0 if it was 0 to 2 pi. Okay, because from 0 to 2 pi, we have exactly the same amount of positive area as we do negative area. So that makes me feel like something went wrong in our calculations, and maybe I need to rethink. Ooh, open the last one. Okay, so sine of pi, sine of 0. Hmm. Definitely am confident that those are both 0 and that this is supposed to be 0. Oh, we're evaluating its sine, but this is originally the cosine function. So we're really trying to find from 0 to 5 of cosine area under the curve. So let me change this to the cosine function. That's where I messed up. I was looking at the antiderivative and not the original problem. So here you can see that for cosine, we have calculated a positive area and a negative area, and hence them being the same sizes gives us an outcome of 0. That makes total sense. Yay. Okay, let's see what other examples we might have. This isn't sharing. Hold on. Share my PowerPoint. There we go. Okay, let's talk about the properties of the definite integral now that we've run through quite a few examples of how to compute them. So if you are looking at the integral, you can make it a negative by switching the parameters. So putting a down here and b up here if it was the opposite before. Also, if you are taking an integral from the starting point and never left home, so home to home, you obviously didn't go anywhere. So the integral will always be 0. And these are all rules, so you can split integrals of terms between addition and subtraction. If there are any constants, not variables, but constants, numbers, not variables, can be taken out of the integral and applied later. If we split an integral at point C, we can add the integrals and get the full integration from A to B, which I demonstrated with home and store example. Okay, that sums up section 5.2 for today, and I will see you guys next week for some more chapter 5.